Now, we can gain a significant insight from a state which is known as plane stress. Now, plane stress is when we have a two-dimensional stress element. It means that the stress that's in the z direction, the sigma z, is 0 in this case, and any shear stresses pointing in that direction are also 0. So this makes things a lot easier because now we're down to a two-dimensional system. Now, if you're wondering, well, this never happens, it actually does happen. It happens in flanges, it happens in pressure vessels, and if a piece of metal is thin enough, you can do some very, very good and very, very accurate calculations to using a plane stress state. Also, this is just going to help us as we're developing our equations. Now, as a note, one thing you should also be able to see from this is that if we're going to maintain equilibrium for this stress element, this very, very small element, then all of your shear stresses, they have to be the same. So tau yx is equal to tau xy. Okay, that is one little key element here that you need to remember. Don't forget that. Now let's figure out some equations to figure out what happens if we were to rotate this stress element. Because we've done that in the past. We had like the section, and then we cut it right here, and we figured out the normal and the shear stress. Well, a very similar case can be found here. Even though we have multiple normal stresses and multiple shear stresses, we can still figure out exactly what those normal and shear stresses would be if I were to rotate the stress element a little bit to the angle. Or, as I show it here, you can just cut it in half. So when I do this, I'm going to have an nt coordinate system, n being normal and t being tangent to this new plane. And using that, you can develop transformation equations. Now here they are. Now, as a note, I'm not going through the derivation of this. It's in your textbook, and if you want to go over it, you can. Feel free. But some big things to notice here is this. First off, this is the average normal stress. Same right here. Average normal stress. This is half the difference. Okay? So the average normal stress is something you're going to see a lot, and that's very, very important later when we get to something called Mohr's circle. But for now, you should write down these equations. These are very, very nice, very, very simple equations. And here's a little diagram that shows just a little bit better what's going on after we've cut it. And if you wanted to, you could even derive these equations using this little diagram right here. Now, so far we were talking about stresses, and I know I'm jumping to chapter 13 now. But I want you to realize that everything we just did, all these equations right here, well, guess what? We can actually use them to develop equations for strain transformation as well. And they're almost identical. Now, I said they're almost identical. They're not quite. They're very, very similar. So if you know one set, you pretty much know the rest. So let's look at here. What's the difference? Well, if you look at it, the biggest difference is right here, right there. That's a minus sign, this is a positive sign. Also, instead of having our shear stress, which is just an absolute shear stress, this one right here is half of the shear strain. But still, you still see similar things. You see, okay, right here, that is my average shear strain. And for the second equation, the only real difference here is that instead of having shear stress, we have shear strain divided by 2, okay? That divided by 2 is going to come from how it's formulated. And if you want to, you can look at your book to see exactly why it's divided by 2. But for our case, it's not super, super important. You can just look at that and realize it. And that's, again, just pointing out those differences. Okay, so I think we'll stop here. We'll jump back into it next time with principal stresses and strains, which is a wonderful and interesting concept. Thank you for listening. I'll see you all later. Bye-bye.